So like I said at the start of class, the notes that we take today should wrap up all the different types of calculations that we have for this particular chapter in our book. So first off, equation up on the board. Delta H of a reaction is the products minus the reactants. That's the simplest way of putting this. For all of you calculus lovers out there, that little symbol at the start of it is a summation symbol. So in other words, we need to know the sum, this little guy right here, of all the heat of formations. Again, the goal of the Progel packet wasn't to complete it, although after notes today, you might be able to complete it a little bit easier if you did choose to go over the rest of it, is to get you familiar with the fact of what are these delta H values, these heat of formation values. N stands for the number of moles, so in other words, if you have a balanced equation, twice as much of something should give off twice as much heat. So we have to take into account the stoichiometric coefficients. Again, this equation is given to you, products minus reactants, on the AP sheet. You would not be expected to know the heat of formation values. Instead, you would be expected to plug them in. Boy, if we had this type of question on a test, this would be the easy stuff. Because, hey, here are the heat of formation values, now solve. Plug and chug math is what needs to help us out. By the way, I believe the website has a couple of questions like this. And you might need, again, that appendix in your textbook to help out with that. I don't think you need to write this down. So instead of wasting time and writing down this second bullet point, what I'm going to be going over today is there's two different ways to use some of the enthalpy math that we're going to do. One's called the direct method, one's the indirect. This is the direct method. So in other words, we can calculate the enthalpy of a reaction from each individual component's enthalpy value. But again, not anything that's noteworthy. Appendix 2 in your textbook is where you're going to find these values. So again, I wrote up on the whiteboard today, that's in A5 through A10. The goal is to actually use this with the lab activity that we're going to be doing later on today. That appendix is something that we will get used to using the further in the year we go because we have to find more and more of these values. What I'm going to do, so again, don't write down this, but I'm going to switch over to Smart Notebook here, and I'm going to show you a sample problem. So this question says calculate the enthalpy of a reaction between solid aluminum and iron 3 oxide, making aluminum oxide solid and liquid iron. This is actually the reaction for something called iron ferrite. So we're making basically lava. So I will switch over and show you how to do this particular problem. So right here is that question again. First thing I probably want to do is write out the reaction. So aluminum plus the iron 3 oxide, which is Fe2O3, making aluminum oxide Al2O3 plus Fe. I then need to balance my equation. So 2 aluminums, 2 irons. From there, it is products minus reactants. I would have to look up the value for the Al2O3. I'd have to look up the value for the iron, liquid version. Maybe I should have included a phase notation for that guy. And subtract the reactant side. So, if I did that, 1,669.8, this is kilojoules per mole, plus 2 times 12.40. That is all of my products. Again, this is just a matter of looking it up on your appendix. Subtract from that all the reactants. 2 coefficient for aluminum. However, aluminum as a solid is its most stable state, so that's why it's given a value of 0. And then the iron 3 oxide I have as negative 822.2. My delta H for that reaction is negative 822.8 kilojoules per mole. So this is the first type of calculation I needed to go over. Boy, you guys can tell that that's flickering too, right? I wonder if it's going to show up that way when we record it and play it back for third hour. How obnoxious is that? Ah, we're going to go with it anyways. What can we do? Back in my day when we had slide projectors, we never had this issue. So, part 1 of the math, seem okay? Again, Pogopak was just trying to show you where do these numbers come from, the most stable state being the 0 version of it. Again, just man made up 0 value, but what's important is the comparison between them. Hess's law. Hess's law is going to deal with the second calculation we have to go over today, and this one is a little trickier. Hess's law basically states it doesn't matter how you get from point A to point B. You can do it in one step, you can do it in multiple steps. The key is you have to be able to get from point A to point B. And this then refers to what we call the indirect method, which again, I don't think you need to write down what the indirect method states. It states that you can solve for the enthalpy of a reaction if you know the enthalpy of a small series of steps. So what we're going to do is one of the questions on the practice sheet you picked up on the way in. So you can either put it in your notes or on that practice sheet that was titled Standard Enthalpy of Formation Worksheet. Here. Before I move into this problem, I want to remind you of something that to me is kind of analogous to Hess's law that we're about to do. Remember last unit where we had to write down an oxidation and a reduction equation. So for example, we had the oxidation of hydrogen peroxide to make 8O2 plus 2H plus 2 electrons. We had the reduction of the permanganate polyatomic ion. And I know this was on a quiz or a test at some point. Remember, we had to, at some point, write the net equation. What we had to do in order to make these two work was we would first multiply each reaction by something in order to get the electrons to cancel out, and then we'd add them together. So, for example, we'd multiply this by 5, we'd multiply this by 2, and then we'd add these two equations together to get our net equation. Hess's law dealing with heat of formation is kind of analogous to that, where if I give you a series of steps, so again, either on this practice sheet, this is question number 1, or in your notes, here's a series of steps. I can use those series of steps to solve for the reaction that I want to know. Question number 1 says, calculate the standard enthalpy of formation of acetylene, C2H2, from its elements. So, if I was given a problem like this, formation of acetylene from its elements. Carbon plus hydrogen makes C2H2. That's the equation that I want to solve the delta H for. Although that's not balanced, so I should probably balance that equation by putting a 2 in front of the carbon. Instead of looking up in our text, what is the heat of formation of carbon, for hydrogen, for acetylene, I'm given the 3 reactions shown on that page. What I can do is similar to what we did with redox, of multiply these equations by things to allow them then to cancel out stuff. I add it all together, it gives me the equation that I want. Here's what I mean by that. If I look at this first equation right here, the graphite plus oxygen makes carbon dioxide. I notice that there is a carbon in the reactant side, bless you, just like there's a carbon in the reactant side of my equation that I want to solve for. However, how many carbons are in the equation that I want to solve for? 2. That means I need to multiply this first equation by 2. Now that means I have 2 carbons, I have 2 O2s, I have 2 CO2s, but perhaps most importantly for us, that means I need to multiply the heat of the reaction by 2. Twice as much reactants should create twice as much energy. That's why I multiply this by 2. That gets me negative 787. Let's look at the second equation. I notice that I have hydrogen on the reactant side. I have hydrogen on the reactant side here. There's 1 hydrogen in the equation given to me. There's 1 hydrogen in the equation that I want to get. I kind of like that second equation just as it is. What I'm basically trying to do is look for the parts in the 3 equations given to me and use them to help me make the equation on the bottom. And the second one, I like it as is. So I'm going to keep that as negative 285.8. Third equation. Here is my acetylene, my C2H2. My C2H2 is on the product side of the reaction I want, however. What should I do to that delta H value so I kind of flip it? In other words, to get my C2H2 on the product side instead of the reactant side. Make it the opposite. If a forward reaction is exothermic, a reverse reaction is endothermic. If I multiply by a negative, I can make that happen. I can flip the direction of the reaction. This is actually something that we went over, I think it was day 1 of introducing these types of reactions. There's a second issue, however, with that third equation, is that there's a coefficient of 2 in front of the acetylene. I need to cancel that out. So to cancel that out, I can multiply by 1/2. Because now that makes this a 1 value. It's kind of weird, but that's going to make this 5/2. It's going to give me 2 CO2s instead, and only 1 water. Which means I need to multiply this by negative 1/2. That gives me a value of 1299.4. If I were to now add all 3 of these values, it would give me the delta H of the reaction, which in this particular problem is 226.6 kilojoules per mole. The first calculation I showed you of, hey, just look up on the appendix, plug in and solve products minus reactants, AP chemistry students have no issue with that. This is the method that is a little bit more complicated. That I need to take 3 reactions that are given to me and turn them into a different reaction that I want to solve for. Now, some students would even say, but wait a minute. I see, okay, you saw 1 carbon in the first reaction, you multiplied by 2. I don't like what you did at that acetylene, that 2C2H2 multiplying by -1. That feels weird. And then a half. But what about the oxygens? There's oxygens in all 3 of these equations, yet there's no oxygen in the equation that I solve for. Same thing can be said for carbon dioxide. Same thing can be said for water. The reactions that you will be given in order to solve an indirect problem like these Hess law problems for enthalpy, everything that is not in the equation that you want to solve for will cancel out. I mean, if you look at this right now, I have 2 O2s here on the first equation. I have a half an O2 on the third equation. I'm sorry, in the second equation. So 2 plus 1/2 is 2.5 oxygens. This 5/2 is a negative 5/2. They all cancel out. The equations that you will be given in any of these indirect models, everything cancels out except for the things that you want. Similar to electrons are going to cancel out when we multiply things out, so we don't even have to worry about them at the end. To me, it's a very analogous situation to what we did with redox in the previous unit. But I know this is the trickier of the 2, which is why, again, there's a worksheet with other problems on here that at the end of the hour, if you have time, you can practice. I believe of the 4 total questions on WebAssign, 2 of them are this method, 2 of them are the previous method. We have questions on this. I have 2 slides to go that are not math-based. They're more just explanation-based to go over. So if we can go back to the PowerPoint then. Today in the lab, you're going to be solving for the heat of solution. Sometimes when you put a solute in water, energy is given off. Sometimes when you put a solute in water, energy is taken in. Whether it is exo or endothermic, deals with attractive forces. This is one of the things I kind of talked to some of the people up front when we were going over some of the Pogel packet. My second big bullet point says lattice energy. Now that symbol of U, you're not going to see this really in a calculation sense. Lattice energy is referring to the energy needed to separate a mole of an ionic compound. The very last dash point on this slide says heat of hydration. To hydrate yourself means you drink water. Hydration in a chemistry sense is interacting with water. Whenever you have a dissolving of an ionic compound, like you're going to be doing in the lab in a little bit here, there's multiple steps needed in order for this to occur. First step is if I take a solid ionic compound, let's call it salt, sodium chloride. The Na plus is attracted to the Cl minus. In order for an ionic compound to dissolve in water, I have to separate the Na plus and the Cl minus. To separate 2 things that are attracted to each other requires energy. That's what lattice energy is referring to, folks. Just, hey, how much energy is required to pull these 2 things apart? So when I give you on that second last dash point a delta H, apologize for the fact that it's lowercase instead of uppercase, because enthalpy should always be uppercase H. When I give you the delta H of a solution equals the lattice energy plus the heat of hydration, that U value is always going to be a positive value. How much energy do I need to put into this to make things that are attracted to each other pull apart from one another? Once you've separated the Na plus from the Cl minus, now water can surround. Think back to Chem 1 when we draw the dissolving of ionic compounds, where you have your Na plus in the middle and then water's all the way around. Water goes all the way around because the partial negative of oxygen is attracted to the Na plus. When there's natural attraction that occurs, things can become more stable. And in doing so, when you go from unstable to stable, energy is released. That's why my very last thing that I mentioned on this slide is that heat of hydration is a negative value. Energy is given off. So again, if I kind of write that out for you here, if I started with solid sodium chloride, and it became sodium ion dissolved in water and chloride ion dissolved in water, it takes energy to break apart the solid ions. That's what lattice energy is referring to. When Na gets surrounded by waters, energy is released, and this is our output then instead. In thermodynamics, positive values mean you put in energy, negative values mean energy is given off. That's why in that slide I said heat of hydration is always a negative value. What you are going to find over the course of our working with thermodynamics is sometimes an overall reaction or process, whatever it might be, is an endothermic process, meaning you have to put heat in to make it happen. That is a net thing. That means overall more heat was put in than given off. But in anything that we do, there's always going to be input and output. It's just a measure of which one is bigger and which one is smaller. Last slide. Remember diluting. We used to do this calculation-wise. M1V1 equals M2V2. Sometimes diluting substances can give off energy. A perfect example, in your safety contract, it says to never add water directly to concentrated acid. So for example, that nitric acid that we worked with when we did the brass lab, we would not want to dilute that by just adding water directly to it, because that process is extremely exothermic, so much so the acid starts to boil. Boiling acid is not a good thing. Acid alone is dangerous. Now we're going to have it boiling and splattering all over you. I made applesauce this weekend, and that was splattering all over us. That wasn't bad. Boiling nitric acid, bad. That's why you'll hear the saying, do as you oughter, add acid to water. When you dilute, you actually have to add the acid to the water, because then there's more water present than acid, so it can absorb more of that heat. Water, really good at absorbing heat, has a high heat capacity. So this is where our notes finish, so I'll pause this in a second here, especially for the third hour people, then to finish up what they have to take for notes. And then once you jot down this, I want us to get out the packet from last class. Because what we're going to do is an example of a heat of solution, dissolving potassium nitrate in water. So again, jot this down. We'll pause the video for a second, allow people to get their packets back out again. Then we'll go over what you have to do for that as well. Okay, so on the third page gives you a very simple procedure. Please make sure you choose the right solid. The trays are set up not only for today, but for next time. We are using potassium nitrate, KNO3. Do not be dissolving the sodium hydroxide today. You will need distilled water, that's in the jug. So it's Pretty straightforward where it says procedure, dissolve 5 grams of KNO3 in 50 mils of distilled water. Remember, we have our calorimeters, our styrofoam cups. You will need a thermometer for this. So when I mentioned take a moment to identify what measurements you need, perhaps what will help out is if I go over the procedures on the third page. I'm sorry, not the procedures, the calculation on the third page. So turn the page to the fourth page. Oh. What's worse, now it's recorded, now third hour gets to listen to me just flubbing up page numbers. We're on the fourth page. Number 1 says calculate the Q of water. Remember, to calculate the Q of something is Q equals MC delta T. Now, if I'm asking you to do this for the water, that mass we might need for the water. So when we're thinking about what data to collect, just like some people in the last lab did not get all the measurements that they needed, people would come in, hey, I forgot to measure the volume. You need measurements to do calculations. I do put up on the smartboard here the C value for water is 4.184 joules per gram degree Celsius. Delta T, what's the change in temperature start to finish? So that gets you calculation number 1. Calculation number 2, whatever the water gains is what the solute lost. Or whatever the water lost is what the solute gains, depending upon is this endothermic or exothermic. So on that page 4, calculation number 2 is just putting a negative sign in front of something. Calculation number 3, converting to kilojoules. Well, again, that shouldn't be anything tricky. We're just doing a metric conversion. Calculation number 4, calculate the moles of solute. Solute is the solid that you're working with, the KNO3. So in other words, you will have a certain number of grams, which is approximately 5 grams of KNO3, and you're going to have to do a mole conversion. The reason why you do that is then to lead us into the 5th and final calculation. Q represents heat for any process. Delta H, however, is your kilojoules per mole. So delta H takes that Q value that you solve for. How much heat did the water absorb or give off? Divided by the moles of the solute that caused that to happen. So I tried to lead you through these 5 conversions, or 5 calculations rather, in order to solve for the delta H of the dissolving of KNO3. If you can do that, then you can also do the follow-up questions afterwards, which is going to have you use the appendix to try to find what's the known value. It's kind of similar to the math that you're going to be doing next time in the lab that's actually a lab report, which is why it's nice to work on this today. If you were to check my answer key, keep in mind that, again, my answer key is based off of last year's textbook, so perhaps the heat of formation values that I found last year in the textbook are slightly different than what our new textbook has. But what we have for today, the rest of the hour, is for you to perform this very simple, brief procedure. One person mass out the KNO3, one person get the water. Hey, let's get our measurements. Let's swirl and mix until it all dissolves and the temperature change is complete. Dump it down the drain for cleanup. Then do math. Do you want goggles and apron because of the KNO3? Otherwise, find something to work with and get going.